Okay, 7.2 is properties of rational exponents. Now, the nice thing about this is we've already done all of these properties. We just didn't do them with rational exponents. Okay, we didn't do them with fractions. Okay, we know that if I have x to the third times x to the fifth, you do what with your exponents? You add them. That would be x to the eighth, right? Okay, the difference is now we're going to do x to the 1/3 times x to the 2/5. You're going to have to add those. But to be able to add fractions, they must first have what? Common denominators. What would your common denominator be between these two? 15. So I need to multiply this one by 5. So you actually have 5 over 15. And this one by? So you have 6 over 15. So your answer is actually x to the 11 over 15. Okay, your properties are exactly the same. That's what's nice about this. The hard part is they're fractions now. Okay, and I know how much everybody loves fractions. Hey, I've been there. Fractions about made me fail my 8th grade year of math. Okay, so same properties. Okay, we'll go through these real quick. Okay, and then we'll just start working some problems because that's what will really benefit us. Okay, so looking here in that green box, the first property, when you multiply two things with like bases, what do you do with their exponents? You add them. Okay, second one, when you have a power of a power, okay, you have something a to the m raised to another power. You do what with those two things? You multiply them. Okay, multiplying fractions is actually easier than adding them, right? Okay. If I have this, that exponent belongs to what? Both of them. Okay, be aware of that. That m goes with the a and the b. So if I had 3x to the 1/3, that's 3 to the 1/3 and x to the 1/3. Okay. Well, what is this as a? What would 1/3 be as a radical? The cubed root. So would it also be possible, excuse me, to write it like this? Yes. Okay, you just got to read your directions and figure out how they want their answers. I imagine that would be really loud if I coughed on that. All right, number 4. If you have a negative exponent, you do what with it? Move it. If it's on the bottom, it goes to the top. If it's on the top, it goes to the bottom, right? Okay, number 5. If you are dividing, so you have a to the m over a to the n, you do what? Subtract your exponents. Do your bases have to be the same to do this, though? Yeah. If this is an x and this is a y, you can't do that. Okay, but if they are the same, then you would take a to the m minus n, right? Okay, again, just quick reviews here. And then the last thing, if you have a over b to the n power, that n goes with what? Both of them. Okay, so keep all those in mind. Those of you who weren't in this class first semester, you might want to get those properties down. All right, example 1. I'm not going to do the examples they give you there. I'm going to do the ones that I have in my book that you don't. That way you have more examples. Okay, but I have 6 to the 1/2 times 6 to the 1/3. Can I combine those? How do you know you can combine those? The base is the same. They have the same base, right? So I'm multiplying with the same base, so I know I'm going to have 6. Okay, but to add these, I have to have a common denominator, which is going to be 6. So this one's going to be 3, 6. This one's going to be 2, 6. So I get a total of 5, 6. Now, they might ask you to write it in radical form. So it'd be the 6th root of 6 to the 5th power. Hey, if they don't ask you to write it in radical form, you can leave it just like this. Okay, just read your directions. They'll tell you what they want. Okay, your first set of directions just says simplify the expression. So do you need to change it to radical form? No. Okay, next one, B. I have 27 to the 1/3 times 6 to the 1/4, and all of that squared. Okay. Now, before you do anything, I'm going to strongly suggest that you simplify anything that's possible. Okay, and this is where we're going to have to start noticing things. 27 to the 1/3 is the same as the cubed root of 27, right? What is the cubed root of 27? 3. Okay, so we need to get to a point where we can notice that. Because now I have 3 times 6 to the 1/4 squared, correct? Okay. And then I do what with my squared? Distribute it. So I have 9 times 6 to the... How do I do that? I multiply, right? 1/2 times 2 is... Or excuse me, 1/4 times 2 is 2/4, which reduces to 1/2. Can I combine those two things? No. Now, if you wanted a decimal, yeah, you could, right? Okay, we don't want a decimal. We want to leave things in exact answers. So you'd have 9 times 6 to the 1/2. Or 9 times the square root of 6. Okay, so that would be an acceptable answer in this case. 4 cubed times 2 cubed to the negative 1/3. What is the first thing you notice? The negative, probably, for most of us. Okay, so that all needs to go where? To the bottom. So I actually have 1 over 4 cubed times 2 cubed to the 1/3, right? Okay, what is 4 cubed? 64. 4 squared, 16. Okay, so I have 1 over 64 times 8 to the 1/3. Okay. That 1/3 goes with both of them. So I actually have 1 over... 1/3 is the same as what? The cubed root, right? So don't I have the cubed root of 64 times the cubed root of 8? Are both of those perfect cubes? Yeah. Cubed root of 64, 4 times 2, which is 1/8. Now, there is multiple ways at times to get to these answers. Okay? One thing you could have done is rerouted here. Okay? Could you have distributed this first? Yeah. Now, some people aren't going to do that because we're taught order of operations and says do the parentheses first and then your exponents. Okay? But if I would have distributed this, and it's one of those things, you're just going to have to see it. Okay? You're going to have 1 over, well, what is 4 cubed to the 1/3? Just 4, because 3 times 1/3 is 3/3, which is 1. So you have 4 times, same thing there, 2, which is 1/8, right? Yeah, and then you still would have got 1/8, wouldn't you? Yeah, so what Mitch is saying is you could have diverted here and done 1 over 512 to the 1/3, and then that would have came out to 1/8 as well. You're going to have multiple places where you can change and go a different path than somebody else. Okay, that doesn't mean you're wrong, it just means you're doing it in a different way. Now, are there wrong ways to do it? Yes. Okay, so you just have to be confident in your math skills and make sure you're doing properties that we know. Don't be making up properties. Okay, I have 6 over 6 to the 3/4. Okay, students have struggled with this in the past because we don't know what to do. But you have to understand these bases are the same, right? So what should you do with the exponents? Subtract, because we're dividing. What is the exponent on this? 1 or 4/4, right? Isn't that the same thing as 1? Okay, so what is 4/4 minus 3/4? If I wanted you to write that in radical form, it'd be the 4th root of 6, right? Okay. Okay, one more out of this set of examples here. 18 to the 1/4 divided by 9 to the 1/4, all raised to the 3rd power. Now what? Nope. Well, so what we're going to take a look at, if you have the exact same radicals, then you can do what Colton was talking about. Okay? So, if these are exactly the same, okay, then yes, you can do it, because that would be like the 4th root of 18 over the 4th root of 9, correct? Hey, we haven't worked a lot with the 4th root, so Colton, actually, your answer is yes. What we would have known that if I had the square root of 12 divided by the square root of 2, I can divide those, right? Because they're like terms. Okay, same thing over here. These are like terms now. So like Colton was actually telling us, the 4th root of 18 divided by the 4th root of 9 is actually the 4th root of 2 to the 2nd power. Thank you. Okay, which this would be 2 to the 3/4, right? Okay, you don't have to change it into a radical form. You just have to look and understand that those have to be the same. I said no initially, Colton, because I didn't immediately notice that those were the same. Okay, but these have to be exactly the same to be able to combine these. Then you can't do it. You wouldn't be able to simplify. Maybe there's a different route you could take. Maybe it would have something to do with your exponent out here. I'd maybe distribute that first and see what happens. But if that was like 18 to the 1/4 and 9 to the 1/3, you'd be done. You wouldn't be able to do it because they're not like radicals. Okay? Okay, and that's kind of what they have there on example 2. Okay, so we're going to try to get through this page on page 408, and then we're going to stop and do our assignment. Okay, but example 2 there, okay, actually that's not example 2 yet. Okay, but on example 2, they give us the cubed root of 25, and this is not one that you have in your book, and the cubed root of 5. Okay. Can I combine these two things? Yes, because I have the same radical, right? So 25 times 5 is? So I have the cubed root of 125, which hopefully at this point we know is 5. Okay. The point they're getting at in this example is make sure you are looking, these numbers have to be the same to be able to combine, correct? If one happened to be a 4 or a 2 or whatever, it wouldn't work. They have to be exactly the same. Okay, so, and then same thing if you were dividing, just like what we just did. That's where we're actually going next. We're getting there. Okay? So calm yourself, Mitch. Alright. Example 3. Okay, that's kind of starting to get into what Mitch is talking about. I have the 4th root of 64. Okay. We have to figure out, basically you need to reduce this, is basically what we're doing. We got to take out not a perfect square, not a perfect cube, but a perfect 4th root, right? Now, thinking of perfect cubes, those get big really fast, right? Okay? So perfect 4th roots are going to get big even faster. So is there going to be very many things that go into 64 that are perfect 4th roots? No. So you probably need to start with 2 times 2 times 2 times 2. Which is what? Does that go into 64? Yes. Okay, so the book teaches it differently. I would rather you just do it like we've always done reducing radicals. Okay, so you take out a 4th root of 16. And that's going to be times the 4th root of 4. 4th root of 16 we said was 2. Can you take any 4th roots out of 4? No, if there's a square root you could, but it's a 4th root. Okay? So you're done. So your final answer is 2 4th roots of 4. Okay, do it just like you would have reduced a square root, except you have to understand what you're trying to take out. Does that make sense to everybody? No? Let's do another one then. Let's do the cubed root of 54. Since this is a cubed root, you want to take out what? A perfect cube. Okay, well our perfect cubes, 2 times 2 times 2 is 8. Does that go into 54? No. So 3 times 3 times 3 is? Does that go into 54? Yeah. So I'm going to take out the cubed root of 27, which would be times the cubed root of 2. What is the cubed root of 27? 3. So my final answer, 3 cubed roots of 2. If we don't quite get that, you'll have to talk to me, because that's the same as reducing just square roots that we've done many times since geometry. We're doing it like crazy in geometry right now. Alright. Now, what if I get something like this? I have the 4th root of 7/8. They want me to reduce this. Now, we have worked with this a little bit. The problem is that if I have this, isn't there a radical in my denominator technically? Because isn't this the 4th root of 7 and the 4th root of 8 on the bottom? Isn't that a problem to have a radical in the denominator? Right? Okay, that's not okay. So, I want to split this. I'm going to rewrite this as the 4th root of 7 on top, divided by the 4th root of 8. Okay? Now, in the past, we've just multiplied by whatever this was. Okay, so put this on hold for a second. Let's say I had the square root of 7 divided by the square root of 3. Okay, I multiplied this by the square root of 3 over the square root of 3, right? Anybody remember what that was called? That was called rationalizing the denominator. Sound familiar at least? Okay. Now this worked because when I multiplied 3 and 3, didn't I create a perfect square? Which I then square rooted, right? Because technically I got the square root of 21 divided by the square root of 9. That's a perfect square. It goes away to 3. Okay, that's what we want to happen up here, but do I want it to be a perfect square? No, I want it to be a perfect fourth root. Because it's got to be a perfect fourth root to go away, correct? Okay, so back up to this problem. 8 is already a what? Isn't that already a perfect cube? With what? 2. Isn't this the fourth root of 2 times 2 times 2? Isn't that the same as the fourth root of 8? Right? How many more 2's do I need to have a perfect fourth root? I just need one more, right? Because I already have 3 of them. So I need to multiply by the fourth root of 2. Hey, this is where things get a little bit interesting. Because now how many fourth roots of 2 do I have? Doesn't that create a perfect fourth root? Okay. The fourth root of 7 times the fourth root of 2 is the fourth root of 14 over the fourth root of 16, which happens to be 2. Okay, so it's almost like what rationalizing the denominator with a radical on steroids, right? Basically, it's a souped up or juiced up version of rationalizing the denominator. Okay, let's do another one of those just for practice. Let's do the fifth root of 3/4. This one's actually in your book, so try not to look at that. Let's try to get this one solved. Okay, break it up, right? So I have the fifth root of 3 divided by the fifth root of 4. Okay, but I know I need how many? I need something 5 times, right? Now, could you multiply by the fifth root of 4 times the fifth root of 4 times the fifth root of 4 times the fifth root of 4, so you have 5 fifth roots of 4. You have 4 here and 1 here. But why would that be silly? That's a lot of bigger numbers, right? Can't I split this into 2 2's? So how many more 2's do I need? I need 3. So I need to multiply the top and the bottom by the fifth root of 2 times 2 times 2, right? Which is? That's 8. Multiplying, remember. Right? Okay, if you want, you can just go like this. Because what's going to happen? What's your answer on the bottom going to be?
2.
It's going to be 2. Okay? So I should have the fifth root of 24 over 2. Okay? Double check. Is there any fifth roots that come out of 24? 2 times 2 is 4 times 2 is times 2 is times 2 is 32. So the smallest one doesn't even come out of there. Okay, so you're done. That's not going to be super easy probably to do, is it? Okay. Like that, Colton? Okay. Everything before this wasn't bad, right? Okay. All right. I do want to do one very last thing. Okay, before we work. I want to do example 4. Okay, we're adding and subtracting roots and radicals. I know there's a lot of stuff. That's why We're adding on tomorrow. We're not going to go on and do new stuff tomorrow. Okay, we might talk about a couple things, but we're not going to do a whole new lesson. We're going to keep working on the same stuff. Hey, if I have, find my extra example 4, I have 5 times 4 to the 3/4 minus 3 times 4 to the 3/4. Okay, there's a lot of different ways you could look at this, but what I want you guys to start recognizing, with us, Devin? What I want you guys to start recognizing is that these two things are identical, right? So isn't that kind of like an x?
Yeah.
So how many 4 to the 3/4 do I actually have? Well, here I have 5 4 to the 3/4. Here I have -3 4 to the 3/4. 5 minus 3. I have 2 times 4 to the 3/4. Okay? Just treat those like variables if you get something like that. Okay? Just look for things that are the same. Even up here, where was this at? With our exponents, we were looking for things to be the same, right? Okay, you're always looking for something to be the same. Those are the same. That's good. Okay, things being the same makes it very easy on us. Okay, now when it's a little bit different, I have the third root of 81 minus the third root of 3. Are those the same completely? No. My radicals are the same, right? Okay, but the other part isn't. But is there a cube root of 81? Or can I reduce it at least? Okay. What is a perfect cube that comes out of 81? 9's not a perfect cube. 9's a perfect square. 27, right? So I can take the cube root of 27 times the cube root of 3. Cube root of 27 is 3. So I actually have 3 cube roots of 3 minus 1 cube root of 3. Okay, this all just came right here. Okay, and then I brought this down. So I actually have how many cube roots of 3? 2. That's a lot of 3's. Now, to make sure we can do this, reduce everything first. Okay? Don't come to something and see this big old number and not reduce it. Okay? If you reduce this first, know that you can reduce this radical. So reduce it, and then you should be able to work your way through from there. But you've got to take the step to reduce first or you're not going to see it. Okay, now I know that's a ton of information in a short amount of time. Okay, I get that. Okay, we'll have a couple days to work on this type of thing. Okay, this is going to take practice. That's the only way it's going to work. It's going to take a lot of practice to get all this stuff down. Just remember, it's the same stuff we've worked on, just now we have different exponents. We don't have nice whole numbers anymore. I know it. Okay, page 411, 23 through 49 odds. Yeah, I think I've said we're adding on tomorrow like at least 3 or 4 times. Come on, Colton.